Hello, my name is Alec Bracamontes, and this is part D of the Proton Mass Project. Now, the relevance of this new unique problem connects directly to our topic because it requires using the actual mass of a proton in a real numerical calculation, showing how precise measurements of proton mass do matter in modern physics. Earlier in the project, we discussed how scientists first measured proton mass and how today's research requires extremely accurate values. This problem demonstrates why even tiny changes in proton mass affect real physical outcomes. Now, the benefits of this problem. Understanding this proton mass problem helps students connect atomic theory to real measurable quantities. By calculating the mass of a specific number of protons, a person learns how microscopic particles add up to measurable values on the macroscopic scale. Solving this type of problem builds core scientific skills such as unit conversion, scientific notation, and interpreting physical constants. It also reinforces the relationship between particles, moles, and measurable mass. Once something can solve this problem, they can handle others, involving atomic mass, molecular mass, Avogadro's number, isotopes, ion charge calculations, and even energy mass conversions in nuclear physics. Now, the development of this problem. I created this problem from scratch by pretty much combining Avogadro's number, real scientific values, and the mass of a single proton by applying them to a sample of hydrogen, 3.0 moles exactly. It's not too simple because it requires multiple steps, like converting, correctly using scientific notation in units, but it's also not too difficult because, the only requirements you need are just the basic multiplication and division that you should already know. But the hardest part, of course, was trying not to make this too trivial, too easy and simple that you could solve this real quickly, and not too complex that it would stress you out and give you a little headache. Now, the uniqueness of this problem. Most of the problems that I found online are pretty straightforward and don't really require a pen and paper. You simply should already know these things in your head. However, this new problem that I created is different because it combines multiple concepts, Avogadro's number, as I mentioned before, the calculation of total proton count, and the total mass of hydrogen, as well as conversions. Now, to make it unique, with some extra information, such as sample size and atomic composition, these were included so that the solver must decide which values matter and which don't. This goes beyond comic textbook questions, and it uses real problem-solving skills, scientific notation, unit analysis, instead of just basic memory. Now, here's a visual for the problem. I created a graph, a total proton mass versus the moles of hydrogen. Now, the significance and relationships. Each data point shows how increasing moles leads to a consistent increase in total proton mass. For example, 3.0 moles of hydrogen corresponds to roughly 0.00302 kilograms of proton mass. The relationship is linear, so the total proton mass in kilograms, moles equals moles times the Avogadro's number and the proton mass, where Na is Avogadro's number and Mp is the proton mass. This demonstrates the practical effect of microscopic constants on a macroscopic quantities and reinforces why precise proton masses values matter. Now, the formula for this problem. The relevant formulas that you're going to need, technically there's three, but you combine the two to get a fourth one. So Mp equals 1.672 times 10 to the negative 27th. And then the total number of protons equals Na times N, which is the number of moles,